Welcome, this is ECE 341 Random Processes, Part 1, Lecture 15. In today's lecture, we're going to talk about families of continuous random variables. We'll spend particular time talking about the uniform, exponential, and Gaussian families of random variables. So let's go ahead and start. A uniform random variable is something we've already seen. We saw it in the discrete case, and there's also a continuous random variable as well. If you think about MATLAB and its rand command, it is essentially giving us a uniform random variable continuous over the interval 0 to 1. So we can define a uniform random variable x, and we'll go ahead and say it's distributed as a uniform. So we'll use a u to indicate a uniform distribution. And then we'll go ahead and say it's uniform on some interval a to b, something along those lines. And if we go ahead from that, we can come up with a probability density function. I'm going to call this fx of x that describes this uniform random variable on the interval a to b. And it's not too difficult, right? If it's a uniform, it should have equal probability on a less than or equal to x less than b, for example. And then we would say 0 otherwise. That interval is of length or width b minus a, and so it's going to be 1 over b minus a as being the overall likelihood, right? That density function. So if I was going to sketch that out just very quickly, I would go from some a to some b, right? And I'm going to have some just uniform or flat density function with height 1 over b minus a, and the total area there is 1, as we'd expect. The integral of a probability density function should be equal to 1. So this is nothing surprising. It's exactly what we'd expect, and it does have a requirement that that b parameter is greater than the a parameter as well. So uniform random variable for the continuous case, it can take a continuum. We can look at things like the mean of this. We've already discussed things like mean and variance for continuous random variables. The mean is just going to be what? It's going to be involving an interval this time, a to b, that's where it's non-zero. And what is it over that? The probability density function is 1 over b minus a. And because it's a mean, we put an x in there. So whatever we're taking the expectation of weights the probability density function, and we add it all up. So we're going to do here a dx. The adding here is in a limiting sense as an integral, right? So if I go ahead and do that, I'm going to end up getting 1 over b minus a, and I'm going to have an x squared over 2. And I'm going to do that on the limits a to b, which if I go ahead and carry that out, that's going to be b squared minus a squared over 2b minus a. And if I do a little factoring there, that b squared minus a squared can be written as b minus a times b plus a, and we're dividing that by 2, right? We have a b minus a. The b minus a's in this particular case, right, are going to cancel, and that leaves us with the final result, that the expected value of a uniform random variable, right, is b plus a over 2. It's the midpoint, right? So if I take b plus a divided by 2, that absolutely will point to the midpoint. If I were going to draw that on my other one, that would be right there. Mu of x is right there in the middle of that guy, no problem. We can also go through a similar exercise. I'm not going to do all the math here. You can see that in the book or online. We can figure out the variance of the uniform as well. The variance is equal to, probably the way that would be most convenient to computing it out would be using this form, expected x squared minus mu x squared, right? Go ahead and do that. And if you go through the integration and simplification steps, what you find you get on there is a b minus a quantity squared over 12, something along those lines. Let's give a very brief example of something like this. So as a very brief example, let's go ahead and think about x being distributed as a uniform 0, 10. Okay, if I was going to go ahead and draw this as far as its probability density function, it would start at 0 and end at 10, and it would be a consistent height, right? It would be a consistent, if I can get my pen here to stop where I want it to, consistent height out there till 10. And what's the overall height there? It's going to be 1 over 10 minus 0, or 1 over 10. So it's going to have a probability density function, f sub x of little x, right? That's 1/10 over the interval 0 to 10. If I go ahead and compute using our formulas before, the mean, so mu of x, right, is going to be, if you take a look at that, b plus a, so 10 plus 0, divide by 2. So 10 divided by 2 is 5, right? That's no surprise right there at 5. That's that balance point on this guy. And if I was going to think about the variance of this guy, sigma x squared on this particular case, we could go ahead and compute that out. B minus A is 10 again, squared is 100, 100 divided by 12. If I go ahead and do that, that is going to be 8.33 repeating, going on something like that. And if I computed out what is the standard deviation from that, I'd see that sigma x is equal to 2.887 approximately. What I'd like to do with this particular one is return to a rule of thumb that we had talked about before. If you recall, we had a rule of thumb. Our rule of thumb was that something like, what was it, 95% of the population, right, of the population was within, right, plus or minus 2 sigma x of the mean, mu x. So if I look 2 standard deviations to the left and right of the mean, I should have 95% of the population. Let's go ahead and take a look at this particular case. If I take mu x plus or minus 2 times sigma x in this case, that's going to be 5, right, plus or minus 2 times 2.887, something along those lines. And what I get out of that is I'm going to get 2 numbers, right? I'm going to get a number that's on the left side, that's going to be minus 0.77, and on the right side of it, it's going to be 10.77. So this rule of thumb says if you look over the interval minus 3/4 approximately to 10 3/4, you should have 95% of the population. How did that work out for us? Well, this 10.77 is maybe here somewhere, and that minus 0.77 is there somewhere, and it's saying, hey, over that interval, we should have 95% of the population. What we see is we actually have 100%, right? We actually have 100%. So in this case, we see that mu x plus or minus 2 sigma x has 100%, right? 100% of the population. So the approximation here isn't perfect for sure, right? It's not perfect, but I will say it's not that far off, even though this distribution is not like what we expected, a symmetric unimodal, so that you have some bell-shaped curve. This one's got a lot of probability out in the tails, is what they're called, out at the edges, and that's going to distort. It's going to distort our rule of thumb approximation here, but it's still not too bad. If it had been perfectly accurate, right, 95% of the population would have been like what? It would have had just somewhere like a little to the left of 10 and a little to the right of 0, right? If we were going to talk 95%, that would be something like, 0.25 from 0 and 10 minus 0.25, something like that. So it's not perfect, but it's not like orders of magnitude off either. So even though we have a pretty sort of non-unimodal, bell-shaped type of curve, which was the basic assumption for making that approximation pretty good, even though this one's kind of a little bit of a more unusual distribution, the rule of thumb isn't horribly off, but it is off, certainly in this case. We'll look later and we'll see some other distributions certainly do a lot better on that. Let's go ahead and switch gears and talk about one other family. This is also a very popular. Uniform, by the way, is probably one of the most used distributions that we have from continuous time. So uniform and Gaussian, or the normal distribution, which we'll also talk about here in a minute, both highly popular. Uniform in particular is used a lot in the generation of random numbers, like on computer algorithms, much like MATLAB's rand command. And the Gaussian just shows up a lot in nature. There's processes that really encourage the expression of Gaussian distributions in nature. Another one that comes up quite a bit is this idea of an exponential. So let's go ahead and take a look at an exponential distribution. So this exponential, we're just going to go ahead and define it through its probability density function. Fx of x for an exponential distribution has the form lambda e to the minus lambda x, and that is for what? X being greater than or equal to 0, and it's 0 otherwise, something along those lines. And here we're talking some parameter lambda greater than 0, right? So you get a decaying exponential. If I were going to kind of draw, a typical type of exponential, it would look something like the following. It would be 0 before 0, right? And then we would just follow this nice kind of exponentially decaying curve as e to the minus lambda x. And at 0, right, e to the 0 is 1, and so we would get out a lambda. So this guy would be lambda at 0, something along those lines. So that's what the probability density looks like here. 0 is it's the mode of this distribution. It's the most likely kind of value. The mean and variance we can certainly do as well. I'm not gonna go through the math on deriving those. You can see those in the book, as well as being able to derive them on your own if you wanted. What we will find on this case is that the expected value of x for an exponential is going to be given by 1 over lambda, and that the variance of x, right, is equal to 1 over lambda squared. I would also make just another comment, and these kind of connections are common, not stuff we're going to use very often, so maybe I will just say this as a fun note, something along those lines. Under this fun note, we might note the following. If I create a discrete variable that is the ceiling, it's gotten by taking the ceiling function of x, then that discrete integer variable k is distributed as a discrete geometric random variable with probability p equaling 1 minus e to the minus lambda, something along those lines. So if you wanted to think about it in a little bit different way, right, this exponential distribution has tight connections to a geometric distribution, which we'd studied back when we looked at discrete random variables. We can demonstrate that this f of x is also valid from the standpoint that it integrates to 1. Maybe that is one we'll do. So if I take the integral from 0 to infinity of fx of x dx, we expect that to be 1. That's an integral 0 to infinity of lambda e to the minus lambda x dx. Integrating an exponential is easy. That's going to be minus e to the minus lambda x, and we are going to do that on the interval 0 to infinity. If lambda was real, then e to the minus, not real, but positive, then e to the minus something positive times a positive infinity is e to the minus infinity. That goes to 0. So this first term goes to 0, and then I'm going to subtract off, but then there's another minus sign, so that's going to become a plus, and e to the 0 is 1. So yeah, we get 1 here. This thing has built into it area 1, as we would have expected. We could also replay that exact same calculation, and instead of doing the infinities there, if instead I had done x, right, and it talked about an accumulation of probability up to some point, something like that, well then I could have gotten the CDF for this exponential, and that CDF ends up looking like it would be, in this case, a 1 minus e to the minus lambda x, and we need a little u of x over here. It doesn't turn on until we get our first possible values of x starting at 0. So it gets multiplied by u of x, something along those lines. So some different relationships that we can do for this exponential. In general, you would want to think about having that probability density function, right? You probably would want to know something about its summary statistics, like its mean and its variance, something along those lines. And the CDF is equivalent to the probability density. It's useful in some cases, but probably not as common as just dealing with that probability density. Let's go ahead and do an example on this one as well. So we'll do a very quick one. It turns out exponential distributions are very commonly employed, or they're commonly appropriate for modeling the lifespan of different things, like maybe a product that is produced by a company. So let's just go ahead and say some product device. So I'm going to just call it a device. A device, right, has a lifespan, a useful lifespan before it breaks, right? A lifespan that is going to be L, we'll model it as a random variable that is distributed, right, as an exponential, right, with lambda equaling, let's let it be 1/3, where L is measured in years. So let's let this be a lifespan measured in years, something along those lines. So we've got this this company, and it produces some device, and its lifespan follows an exponential distribution. Let's further assume that the company, or the manufacturer, maybe that would be a better way of saying it, the device manufacturer offers a 1-year full replacement warranty. So if it breaks in that warranty. If it breaks in that first year, you can send it in and get a replacement done. So a couple of questions we might ask on this. If this device has a lifespan L that is distributed as an exponential, what's the device's average lifespan? What's the average lifespan? How long would you expect this device to continue working? Well, that's pretty easy, right? We're just talking the expected value of the lifespan. And if we go back to what we had said, somebody's already done that calculation. We don't have to go through it. Once we know that we are dealing with an exponential distribution, we can just use it. Although you should also probably be able to carry out that calculation necessary to show that the expected value of an exponential is 1 by lambda. But I know it in this case, so this is going to be 1 over lambda. And I'm going to evaluate at the lambda for this, which is 1/3. So that's going to be equal to 3 years, right? So we expect on average that these devices, last, have a functional use duration of 3 years. Some, of course, are going to not make it that 3 years, and some are going to make it quite a bit longer than that 3 years. Probably the one that would be important to the company, right, is they know that anything that's pretty short in the lifespan is going to be replaced. Like, so you have this thing and it's running for a month, and it breaks. Well, just number one, you're not going to have a happy customer, so probably taking care of some of that is important. But the company does need to manage their financial kind of risk or liability on these products, and so it'd be very much of importance for them to get an idea of what percent would be replaced under warranty. So we might, as a part B, say what percentage of devices, right, would be returned, right, returned under warranty. So really what this is saying, right, what this is really saying is, what's the probability that the life of a particular product is less than or equal to 1 year? So that's the probability that L, right, is less than or equal to the warranty period, which is 1 year in this case. Well, this is a straight calculation. We can get probabilities over intervals by just integrating over that interval the PDF. So this PDF starts at 0 and we're going to end it at 1 because that's the warranty period. And then we're going to go ahead and put in the probability density function, which was 1/3 e to the minus L by 3 dl, right? Something along those lines. If I carry out that calculus, I'm going to get minus e to the minus L by 3 going 0 to 1, which ends up giving me 1 minus e to the minus 1/3. And if I go through all that, I find out it is 0.2835, or about 28.35% of the devices. Let's call it 29%. So just a little under a third of the devices you could expect it to come back under warranty. Analysis on that could certainly be acceptable to the company, but they would have to probably charge prices that would be reflective of being able to handle that warranty work, right? But 28% return on a device is also pretty high. So if I were going to be a consultant for this company and asking them questions, I'd be saying, hey, what can we do to make it so that you don't get as many devices coming back? All right, turns out that there's lots of others. So there's lots of other continuous, that wasn't a very good S, we'll try it again, continuous RV families. I'm not going to cover all of them. I really encourage you to read the chapter 4, which will introduce more than we're going to introduce in the lecture itself. And then there's also just a bunch of tables back in the back appendix that will also lay out a lot of these. So some things that you might look at or that you should do. I think you should read, go ahead and read about these other cases, these others. They're probably not as common as the three that we're going to spend most time talking about, but they still have absolutely application. So there's things like the Erlang. There's an Erlang random variable, and this one really comes from an IID sum. Maybe I should write that different. Maybe I should call that a sum of independent identically distributed exponential distributions. So it's connected to the exponential, which we do know is something that we've talked about in detail. Then there's certainly others. There's like a beta. There's a beta random variable, right? There's something called a Cauchy random variable. There is a gamma. random variable, every one of these has a known probability density function and also has known things like means and variances, all that kind of stuff that would make it easy for you to get up and running and start doing calculations. All you would need is some indication that particular model was appropriate to your situation. There is a Laplace RV. That Laplace, if you take a look at that, it's kind of Gaussian-like, which we will talk about Gaussian. That's kind of Gaussian-like, but with heavier tails. Heavier tails. What are those tails? That's the stuff way out at the edge, right? So if you've got a distribution that's kind of bell-shaped, right? The tails, right, are the parts that I'm shading here. So that's a tail, right? So this Laplace is a lot like a Gaussian. It's kind of bell-shaped, but it's got more probability stuffed out there in the tail. So there's certainly cases that you see that kind of stuff. You can see Laplacian noise and communications applications, for example. There's also stuff like a log normal, right? We are going to talk about the normal here in a minute. There's one called the log normal, and then there's more. I mean, we could keep going on these things. There's a bunch of different ones. We don't want to get too distracted with going through every single one, because most of them you can just take the model once you recognize that it is the one that's needed. And that can come empirically. It can come from somebody telling you. It can come from you understanding the physics of the situation and linking it back to that probability density function. Lots of different ways of doing that. Once you know the model, well, then you just go forward with the calculations. Okay, we have one more that we want to spend some time on, and this is one that we're going to have to spend a little more than normal time because it is number one, a little more important than normal distribution, and it's also a little bit tricky to deal with it. It has some difficult properties that make calculations associated with the normal just a challenge, and so we need to probably do a little more slow down, a little more time in talking about this guy. So this is all going to be under what is called the Gaussian random variable, right? Which is also called the normal. It's also called the normal random variable. So you can use either one of those guys. And this is it's a bell-shaped distribution. Bell-shaped distribution. This comes up a lot. So if you take a look at the overall kind of distribution here, it looks bell-shaped, so it has symmetry about its midpoint, and that midpoint is the mean, right? And it gets progressively less likelihood as you get further and further away from the mean. I will tell you that our rule of thumb, that if you are plus or minus 2 standard deviations from the mean, coming about 95% probability, it's a good estimate. It's a really good estimate when you have an underlying distribution that's a Gaussian. We're not going to prove this. It's in your book. It's at a later chapter. We just aren't going to have time this semester to get to it. But if you're interested, you could certainly go out there and look. I don't know. Maybe we'll do an example of a simulation to show parts of this. But I'm not going to do the theoretical proof of it. But what I'm going to say is a fact established later in the book, and it goes something like this: if you have some sort of random process, and I don't care what the underlying random process is. It could be a uniform, it could be an exponential, it could be Cauchy, it could be Erlang, it could be gamma, it could be Laplace, it could be any, it could be none of those, it could be something else, it could be a derived random variable of those. It doesn't matter. Whatever distribution you have, okay? If you have something that's guided by a probabilistic distribution, if you have a whole bunch of those and they get added together, okay, what is the distribution of that sum thing? Well, something called the central limit theorem, and that's what's proved later in the book. The central limit theorem basically says that when you have a sum of a bunch of random variables, the sum approaches a normal, okay? It's just the way it works out. And so the proof there is not trivial, but it does help explain why normals are so prevalent in kind of nature, because so many things in nature are the result of additive effects, that there's little pieces adding together to make a bigger whole. And there might be some uncertainty or some variability in those little underlying pieces, but when they get added together, they tend to a normal. So if you take a look at just about any kind of characteristic that you could measure with any kind of biological thing, for example. So we talk intelligence, you talk height, you talk weight, you talk, circumference of your head. If you talk about, the length of your middle finger, it doesn't really matter in there. All of these characteristics that are associated with life, right? tend to be the consequence of many underlying little effects taken together in sum. And so you will find very good model consistency with almost all of those kind of measurements to the underlying Gaussian distribution. Is it perfect in every case? Probably not, but in many cases it's exceedingly good. So modeling things like weight and height and other physical characteristics using a normal, very, very common and very, very accurate. So it's absolutely a distribution of interest and something that we should be able to handle. Mathematically, when we start trying to recognize or represent this guy, I'm going to say random variable x is distributed as a normal, so I'll use n to indicate a normal distribution. And it turns out there are two parameters that are needed to express this normal. There's a parameter mu and there's a parameter sigma squared. It's not accidental that we are using mu and sigma squared. We will find later, although we won't prove it, the proofs are a little bit ugly. Well, maybe we'll prove one, but the proofs can be a little bit of a challenge. We will find that mu really is just the mean of this random variable, and the variance is the sigma squared parameter. So a Gaussian is completely determined as far as parameters needed in terms of its mean and variance. If you know its mean, right, and then the variance tells you how much this thing spreads out, right, that's related to the sigma x squared. If you know those two things, you are going to know everything you need to know about defining this distribution that is normal. Okay, so given that, what is the probability density function? So I'm going to give this without proof. The proof obviously would not be something straightforward. This is a little more than the scope of this class to talk about how you would get this particular form, but it looks like the following. Fx of x is equal to 1 over the square root of 2 pi, and then we are going to have our sigma, and then we are going to have an exp, an exponential function, and we will have minus of x minus mu squared over 2 sigma squared, something along those lines. That is the probability density function for a normal distribution. Now, if we go back, if you took an equation like this, if you took an equation like this, so if I took this whole equation sitting there and I plotted with MATLAB, and I did that with MATLAB, using some mu and using some sigma squared, you could easily verify that that guy is bell-shaped with its peak at the mean, and that roughly plus or minus 2 standard deviations would be, okay, 95% of the population, or 95% of the area. And we know the area should be equal to 1, right? So plus or minus 2 standard deviations, if you integrated on that, should be roughly 0.95, something along those lines. We'll do more on that as we go along. There is a comment that we should say here. We should say that standard deviation, just a reminder, sigma is greater than 0. Mean can be anything. You can have a mean that would sit anywhere on that real number line. You could have a mean of minus 40. You could have a mean of plus 187. It can be anywhere on that. But the standard deviation has to be a non-negative parameter. And when you square it to get the variance, that would also ensure that the variance is non-negative, which we know it has to be. Okay, so if we were going to talk about showing that the integral of fx of x from minus infinity to infinity equals 1 is, I'm just going to say, maybe not is, maybe I'll say it requires, effort and maybe a little guidance, okay? I think your book actually has problems that help you through the derivation of doing that. It's also online. It usually involves something like squaring, and squaring this particular distribution, and then like changing to polar coordinates that can oftentimes help in showing coordinates that can oftentimes help showing that this probability density function equals 1. We could do this empirically. You could do with numerical integration, right? Numerically, and with MATLAB. MATLAB has all sorts of built-in functions for doing numerical integration. If you're interested in this, take a look at the quad function. Whoops, let's try to get that a little bit neater. So let's say if you took a look at the quad function as an example, you could For example, go ahead and define your probability density function using something like an anonymous function, and then you could go over here and use the quad function to do a numerical integration of that, and you would see that it would integrate to 1. So lots of different options to doing that. We aren't going to go through the actual proofs on that, nor are we going to go through proofs that the expected value, well, we'll go through one, maybe not both of them, that the expected x is equal to the mean mu, and that the variance of x equals sigma squared. Okay, well, one proof. Let's do one. So let's go ahead and show. I'll pick this particular one. It's a balance of giving some flavor of these guys, but also not like committing an entire effort and focus of this class on nothing more than just proof, which gets kind of a little bit tedious. So let's show that expected x is equal to mu, something like that. Fortunate thing is we think we know where we're going with this, and we have a working definition of what is expected x. So what is expected x? Expected x, right, is equal to, it's an integral over the range space minus infinity to infinity of x times what? The PDF. So that's going to be 1 over square root 2 pi. We have sigma, we have exp, and I have a minus, and I have x minus the mean mu over sigma, right, squared. And I would have a 1/2 out of that as well. So I just combine things slightly different and a dx on that. I'm going to do a change of variable, and part of the reason I'm doing that change of variable is because I know where I would like to go with this. So I'm going to let y equal x minus mu by sigma. We're going to actually find out that this sort of transformation is incredibly important and incredibly common in working with a Gaussian distribution. So if I do that, I know that dy is equal to dx by sigma, something like that. If I start making those substitutions in there, well, if x went minus infinity to infinity and mu and sigma were both finite, y also goes from minus infinity to infinity. So the limits of integration don't really change. If I was interested in what is x, I've got an x over here by itself, right? I've got to solve that expression, y equals x minus mu over sigma, in terms of what is x, right? So I could take that guy and I would get what? I would get something like y sigma plus mu equals x. So I can plug that guy in for x because I'm turning everything over to y, right? So I would have sigma y plus mu in place of that x. I also had in there that divide by root 2 pi, so that's still there. The sigma that was in the denominator though is going to be connected with that dx to give me the dy, right? So we're going to see that sigma in the denominator disappear. And then I have an exp, right? And I'm going to have what? I'm going to have, in this particular case, a minus y squared by 2, right? Something like that. And then I'm going to have dy on that. Okay, well, this is still maybe not totally obvious what it looks like, but I think we can work with it a bit. I'm going to focus a little bit on this sum up in the numerator. So I've got a sum of pieces multiplying things. I should be able to break this up into 2 integrals as a result. So I'm going to have this be an integral, and I'm going to have a sigma over root 2 pi. I'll go ahead and pull that out, and I'm going to have an integral minus infinity to infinity, and I'm going to have what? A y e to the minus y squared by 2 dy. And we'll come in and make some comments about that here in a minute. The other piece is going to be what? A plus. And I'm going to go ahead and I'm just going to think of that. Whoops, I don't want to do it quite like that. Let's see if I can figure out how to get my tools back. Okay, so I want to get rid of that, and I wanted to put it as a colored highlighter. There we go. So that mu part, that mu times all that other stuff. I'm going to pull out the mu and leave all the other stuff inside the integral. So what do I get? I get that mu pulled out, but I still have an integral minus infinity to infinity, 1 over root 2 pi, and I have an exp, right, of minus y squared by 2 dy. Wow, that got kind of tight in there. So let's move this whole thing over if I can grab it. Hopefully I'll be able to grab that, and I'll just move it over where it's just a tiny bit more readable. Okay, so I want to work with this form at this point. I'm going to start with the first one, and I'm going to do a little logicking on this guy. So what is y? Y is an odd function as far as plotting that guy out. If I was going to look at y, right, as a function, it looks like a line basically, and so that's just an odd function. How about this e to the minus y squared over 2? that is an even function. It has even symmetry in there, something like that. So I'm going to be multiplying an odd function times an even function, and then I'm integrating it. The product of an odd and an even is equal to an odd function. Okay, if you take an odd function times an even function, it is odd. And if I integrate an odd function, the integral of an odd function from minus infinity to infinity is what? It's 0, because all the positive area gets canceled by all this negative area. So what we can do in this particular case, by just looking at the arguments of this integral, we can see that we're integrating an odd function times an even function, which means we're integrating an odd function over all time, and that guy has to go to 0. Right? So that first term, a big fat 0, nice way of getting rid of it. How about the second one? I'm going to ignore the mu, and I'm just going to be thinking about this stuff. Oh, let's do that in the highlighter as well. Just thinking about this stuff off to the right. Well, if you look kind of careful at that guy, that looks like the PDF of a normal distribution with 0 mean and unit variance, right? And what happens when you integrate a PDF? Integral of a PDF we know is equal to 1, as long as we know it's a known family. So this whole second part here, right, this guy here is going to go to 1. And we're going to get 1 times mu. And in the end, what do we find? We find that the expected value of x, when x is a normal distribution, is indeed that parameter mu that we use to define that guy. Awesome. Okay, so that's probably enough proofs with that. Let's continue our investigation of the normal, and let's spend a little bit of time talking about linear transformations. So let's do the following further. So I will say further. If x is distributed normal with mean mu and variance sigma squared, then let's take a look at y being equal to ax plus b, a linear transformation on that guy and how it is distributed, okay? What I'm going to do first is I'm going to think about this linear transformation before. We had looked at this. We had looked at a derived random variable y as being ax plus b of a known distribution x, and we looked at things like mean and variance. What is the mean? Well, if I take expected y, that's going to be expected ax plus b, which is going to be a expected x plus expected b. Expected b is just b, so that's going to be a expected x, which is mu x, so a mu x plus b. So we're going to have something whose mean is a mu x plus b. Wow, I already don't like how that's coming out. So let's just go ahead here and say a mu x plus b, right? That's mu y, something like that. How about the variance? The variance of y is the variance of ax plus b. B doesn't contribute to the variance. That was just an offset. We saw that before when we talked about variances and variances of derived random variables that were linear transformations of a known. The variance is a squaring kind of expectation. So the ax is going to give us an a squared, which will pull out. So that's going to be an a squared, right? Sigma x squared, something like that. So that's going to be my sigma y squared along those lines. So we know that if I do a linear transformation on x, right, that the mean and the variance come out pretty easy. They're a mu x plus b, and they're going to be a squared sigma x. What we don't know, and we're gonna delay this. I will prove it later. I will prove it later when we talk about how to compute the kind of distributions of derived random variables. We're not quite ready for it. What we will find later is that it is also normally distributed. A linear transformation of a normal does not change the underlying distribution from being normal. Okay, so I'm going to just note that up here. I'm going to say that this is easy to show with what is called the CDF method, which is coming later. So we're going to delay this proof. We'll come back to this proof because it's an important result, and it's not always guaranteed that when you have a derived random variable that the original distribution survives that transformation, right? But in this case, when we start with a normal and the derived random variable comes from a linear transformation, ax plus b, the normality survives. Now, the parameters change, right? Mu, the mean of it, got changed. It got changed by a mu x plus b, and the variance changed, right? So if a were a huge number, for example, let's say a was 100, the variability there would get really big, right? Because it would go up as a squared, something along those lines. Okay. Now, there is a particular kind of normal that we're going to have a lot of need for, and we haven't quite gotten to why. We will very soon. I'm going to say a standard normal, a so-called standard, what is called a standard, whoops, a standard normal has mean mu equaling to 0 and variance sigma squared equaling to 1. Okay, this is super important. We need to be able to know, understand, and use this thing called the standard normal. It's so important, it will have its own name. So this standard normal is going to be called z, and we're going to say the variable z, or the standard normal random variable z, is distributed as a normal with mean 0 and variance 1, something along those lines. Okay, the reason why it's so important, the reason we're going to have so much use for it, is coming really, really quick. So another note, let's look at another note. Suppose x is distributed as a normal, right? Mu x comma sigma x squared. And now I create a new random variable y that is equal to x minus its mean divided by its standard deviation. That was something that we had looked at before when we did a transformation when we were going through expected x, something similar to that. Okay, so what is the distribution of y? How is y distributed? I could write this slightly different. I could write this as 1 over sigma x times x, right, minus mu x over sigma x. And what I can note is that is the a, and this whole thing, including the minus sign, is the b. So this is a linear transformation of x, and that tells me that y is distributed as a normal, right? Proof yet to be shown on that, but we will take it. And then its mean is what? It's going to be a mu x plus b, right? So it's going to be a, which is 1 over sigma x, mu x, right, plus b, coming in there, plus b. And then we are going to have, in this particular case, what was b? We can go ahead and make that substitution right now. B was, it also had that minus sign, so b was minus mu x by sigma x. Oh, and if you do all of that, mu x by sigma x minus mu x by sigma x, that's 0, right? And then what's the variance? The variance is a squared, right? So the variance is going to be a squared sigma x squared. But what is ax, or a squared? That's 1 over sigma x squared. So 1 over something times a something, that whole thing goes to 1. Okay, I've made sort of a mess. Let's clean it up. Y is going to be distributed as a 0, 1, which means really y is my standard normal, okay? What's the net kind of lesson out of this? If I've got an arbitrary, whoops, I'm going to get this as my highlighter one way or the other. If I have an arbitrary normal distribution, x is a normal with some mean and some variance. If I take that variable and I subtract off its mean and divide by its standard deviation, right, what do I know I get? I know that I get out of all of that a random variable that is the standard normal. It is a normal 0, 1 random variable. Okay, so you have an arbitrary Gaussian distribution. You can transform it to a standard normal very, very quickly. No problem. Very easy to do, right? No problem on that. Okay, so in this particular case, let's talk about why this is maybe so important. Let's look at the CDF of our standard normal z, okay? And by the way, is if I can understand the CDF of my standard normal, right, I will understand the CDF of any normal because I can get to it by linear transformation, right? This CDF of a standard normal is also, just like because of this of the standard normal being so important, it has its own special name. So the CDF of z will have its own special notation. They're going to call this guy phi of z. So we read that as the CDF of the standard normal z. And what is it equal to? That guy is equal to an integral minus infinity to some point z, right? And we have 1 over root 2 pi sigma is 1, so you don't see the sigma. And we have e to the minus And we would normally have our variable z squared over 2, but we're doing an integration. I don't want to confuse that with what's in the limit, so I'm going to put in a dummy variable of integration. I'm going to call that u squared by 2 du. This is a really typical kind of thing. Use a different variable of integration than your variable, right? When that variable is found in the limits. Otherwise, you're going to get messed up somewhere, okay? So the CDF for this is an accumulation of all area up to and including some point Z. If I was going to draw this out, it would look something like the following. We know that a standard normal, right, has this sort of nice bell-shaped curve. We know that this peak is at 0, right? And we know that if we came out here at about 2 or minus 2, the standard deviation was 1, we should have about 95% of the area. The CDF itself says, hey, take a particular value of z, right? So come in here to some value of z, something along those lines. And I would like to know what is the accumulation of probability up to and including that point. So I need to find all of this area up to and including that point, right? So what do? I integrate from minus infinity to z. So minus infinity to z, right, of this guy here, that's just the PDF, right? It's just the PDF. All right, so CDF, no problem. That's just by definition. Here's the kicker on this guy. I'm going to put a box around this, and I'm just going to say the following. No closed form exists. I don't care what calculus book you go to. I don't care what kind of super fancy math handbook you go to. That guy does not have a closed form solution. There is no way that you can just write that as being equal to something, right? Single closed form without the integral. You might be able to get a series approximation that would involve an infinite number of terms. That's not really much in the bargain, but there is no closed form for this guy. What does that tell me? It tells me that computing probabilities of a normal is going to be a challenge, right? It's going to be a challenge because we can't do the integration needed. There's no closed form. You know, if you want to know the probability that a normal is over an interval, right? If you really want to know the probability that a normal distribution is plus or minus what percentage is within plus or minus 2 standard deviations of the mean, you would need to take an integral of this form, or a difference of 2 CDFs would give you the probability of being over an interval. Without a closed form on that, we're going to have some troubles on it. So what has been the classic solution for this? The classic solution has been that somebody goes through and they program a computer and they do a bunch of numerical integration to find values of this CDF, and they do it for the standard normal, knowing that whatever normal you have, you could find its corresponding probabilities by taking that linear transform to relate your arbitrary normal to the standard normal. And we'll go through a lot of examples on that. So let me just include just a couple of details in here, and then we'll see where we can get with it. So I'm going to just say the following. I'm going to say now, okay, with some random variable x being distributed as a normal mu comma sigma squared, right? We know that its CDF, fx of x, is equal to, we can get it from the standard normal as long as x is subtracting its mean and dividing by, right, its standard deviation. How do I get something like that? Well, what is fx of x? Fx of x is the probability, right, that x is less than or equal to x, right? Let's work in that middle. That's the probability. Let's take x minus the mean, right? Less than or equal to, well, then I'm going to have to do the same thing to the other side, x minus the mean, and let's divide by the standard deviation. Divide by the standard deviation. Those guys are equal. That thing on the left, though, right, is just z. If I take something minus mean, divide by the standard deviation, that is the standard normal. So the CDF of an arbitrary, normal distribution, random variable x following a normal distribution, can be gotten by the probability that z is less than some known value, x minus mu by sigma. And that is, by definition, that phi, the CDF of the standard normal, right, of x minus mu x by sigma. So if I know all of these standard normal kind of calculations, I can apply those to find the probabilities for any arbitrary one that I need. Another one that we said, we already had mentioned this, the probability that A is less than some X is less than or equal to B, being on some interval. We know that that's a difference in CDFs, and because I can utilize that standard normal, it's going to be a standard normal of what? I'm going to have B minus mu over sigma, so the rightmost point minus the CDF of A minus mu over sigma, something like that. So I can get probability of being on intervals as a difference of CDFs, and we can get them from the standard normal CDF, right? So finding probabilities for arbitrary normal RVs, X being distributed as a normal, some mean mu, some variance, sigma squared, right? Something like that, can be solved if I know phi of z, right? The standard normals CDF. This guy is available by table. So somebody has gone through and they've computed out values of the CDF across large numbers of points. Okay, this is available by table and also by computer, right? So there's computers and they're good at things like numerical integration. So we could think MATLAB here. You'll probably get a homework problem that's going to allow you to build some MATLAB programs to compute out things like probabilities associated with normal distributions, okay? I will conclude this lecture with one final detail. Next lecture, we are going to go through a bunch of examples of computing probabilities and dealing with a variety of normal distributions, but that will come next time. So what would I like to conclude with on here? I will say that we also have another table, or another table is typical, something called, we also have what is called the standard normal complementary. Oops. See if I can get this guy back up. Need to get that spelled right. Complementary CDF. And what is the complementary CDF? We're going to call it, just to keep with book notation, Q of Z, which is equal to the probability that Z is greater than little z, which is what? That is 1 minus phi of z, something like that. So I can get the complementary CDF, right? The complementary CDF from the regular CDF just by taking 1 minus. That shouldn't be a big surprise in there. Okay, if I was going to look at it in terms of the calculus, it would be something like a 1 over 2 pi, integrate not from minus infinity, but now we're going to go from z to infinity, right, of e to the minus u squared by 2 du, something along those lines. This also, no closed form. So why do I need both of these? Why do I need phi of z and also need q of z? Give me a chance next time to show some examples. I'll also pull up the tables and share those with you. It really comes down to, if I'm figuring out a probability, let me just quickly show what this would look like. Think of a normal distribution, something like this, normal distribution. Using phi for most values is not going to be a problem, okay? But if I start doing, let's say, values here, large values of z, so I'm here maybe, or bigger, something like that. If I want to find the area there, it's going to be, this area is going to be very close to 1, right? And because it's so close to 1, that phi of z is going to give you an answer like 0.999999999, and there's going to be all these nines, and that's just a really inefficient way to show it, where if I do 1 minus, I'm going to get whatever the probability is, right, without all those nines. It just makes easier to get a significant number of digits. So we use the complementary. We are going to use Q, right, when dealing with, probabilities, probs, involving values in the tails. So next time we will do a bunch of examples with this. finish out our work, also look at the tables for the normal probabilities, and then we're going to start a transition to looking at what are called mixed random variables and using what is called the delta function. That'll be next time.